SwayamPrabha. Digital India. Educated India.
Hello everyone. Last class we were discussing about welding induced residual stresses. There at the end of that lecture I was discussing about how to generate that residual stress in a weld cross section. Now today I will discuss about that residual stress first, then I will discuss about what are the influencing factor and control of this residual stress is done in a welded structure. So, this is the content of today's presentation, that means I will cover factor influencing residual stresses and how we can control these residual stresses, that means different types of residual stress mitigation or controlling technique, and at the end I will introduce about methodologies for prediction of residual stresses. So, last class I was discussing in a weld section how the residual stress is discussed, how the residual stress developed, correct. So, there what we observe, that means near the weld zone the residual stress is tensile in nature, and just away from this weld zone that residual stress is compressive in nature. That related thing I will discuss today first. After that I will discuss about factor influencing residual stress and its control. Okay. So, first of all last class related things I will discuss, after that I will discuss this following thing. So, last class what we observe, that we observe that the residual stress is depends on what? Temperature, and it also depends on different other factors, that also I will discuss. That means how the residual stress developed with temperature in weld zone, that first I will just refresh here. After that we will discuss subsequent topics. So, we can draw temperature versus residual stress and strain curve here, like let this axis represent temperature, and let us this axis represent our stress. So, right side I will discuss about stress and left side I will discuss about strain. Okay. How this stress strain behavior developed in a welded cross section with the variation of temperature, that I will show. So, along this direction temperature is increasing. Now, what happens if the temperature increase, just I am just drawing this thing, if the temperature increase, then initially when the plate is in room temperature, at that time the temperature is let us room temperature here. So, at that time, so this axis also represent the temperature, this you should keep it in temperature, that means temperature is this axis also temperature, that means how this temperature is varying, that horizontal axis is represent. So, let this is the room temperature point which I am representing here by point O. So, once this plate is in room temperature, at that time generally here you can see this stress and strain in that plate is not available, that means residual stress and strain is not available in that plate at room temperature. Now, once this temperature increases, then you see this residual stress, let us temperature increases means in weld zone, once this temperature increases at that time, that means at that time with increase of temperature strain is generally compressive in nature, and how it is, that I am just showing here, you can see. So, with increasing temperature it is like this. So, I am just pointing it like this, let this is the point 1, let this is the point 1, let this is point 2, this is point 3 and this is point 4. So, this is the increasing in temperature, this direction represent increasing temperature. So, this is actually negative strain, this side represent negative strain and this type represent positive strain, and this side represent positive stress and this side represent negative stress. This you just keep it in mind. So, once we increase the temperature gradually, you can see in weld zone, then what happens, this strain generally gradually compressive in nature in this zone. Because why it is compressive in nature? Because this zone generally try to expand, but what happens, this surrounding parent metal zone, it try to contract that zone, correct. So, it try to expand, but what happens, it is contracted by the surrounding material, correct. That is why in this zone, once the temperature start rising due to heating, or you can say welding arc, then what happens, you see in this zone there is a start negative strain during heating. So, this strain generally gradually increase up to a certain limit with increase of temperature. After that, what happens, that plasticize start, because after certain limit that zone start plasticize, then this material load bearing capacity decrease, okay, load bearing capacity decrease. So, what happens after that, this compressive stress gradually decreases, and once the material start melting, at that time this melting material does not carry any support. That means any the melting material generally does not support any resisting types of force inside the molten material, that is very well known to you. That is why at that time this compressive stress compressive strain become 0, that means almost 0 you can say. Now, so with this variation of this strain, stress is also what happens during heating cycle. During heating cycle, this stress is also it's compressive in nature. This stress is also compressive in nature. You see, compressive in nature with this with the similar pattern of this strain. And what happens once this on it goes to around melting point temperature, let us here also I am representing this is 0.1, this is 0.2, this is 0.3 and this is 0.4. So, once this temperature goes at the melting point temperature, then stress is nullified in that zone, correct. So, with temperature this stress is also during heating cycle, it is compressive in nature. After that, from this generally once we just start cooling, once we start cooling from this molten state, then what happens, this material in this weld zone try to contract, that means during cooling phase, this is let us heating phase, okay. Now, let this during cooling phase what happens, this molten material try to contract, but this surrounding material generally try to pull away, that means it try to pull away this shrinkage phenomenon of this molten material. This is during cooling. So, as this region is subjected to some tensile types of force due to surrounding material, that is why what happens during cooling, there is a start developing this tensile types of strain, okay. There is a start developing tensile types of strains. Now, what happens, this tensile strain or this shrinkage resistance, generally you can say this shrinkage resistance is gradually increased till the room temperature. That is why what happens here, this shrinkage strain also increasing, like you see, let us say this is 5, then this is let us 6 and this is 0.7, that means it is around room temperature. At room temperature position, what happens, this strain goes its maximum value, which is tensile in nature. How this tensile stress is generated? Tensile strain is generated. This tensile strain is generated because this is trying to shrink, but what happens, it is generally resisting by this surrounding, what it is called, surrounding cool material, correct. Due to this thing, this weld material zone is subjected to some tensile types of force, correct. So, that is why what happens in this weld zone during cooling, there is develop some tensile types of strain. So, that is why due to this tensile strain distribution, here also the stress distribution also gradually it start rising, okay, and it go to maximum value. Okay. It gradually start rising and it go to maximum value. This way we can write. Okay. So, how these things? So, here I am just writing the let this is 0.5, this is 0.6 and let this is 0.7 around room temperature. Actually, I am just drawing like this. So, how this stress strain curve varying with temperature, that you observe. That means, why in weld zone at the end after cooling the stress distribution is tensile in nature, that idea I think you got from this curve. Okay. This is called stress strain temperature curve, this you can say. Now, you see here just I am going to show you how the residual stress distributed over the entire weld specimen, that I am going to show you, because residual stress is a self balancing types of stress you can say, or it is whatever the force developed due to residual stress, this residual stress generated force is self balancing type. That is why here I want to show you how the residual stress is distributed in a weld specimen. Let us here this is a weld specimen, just I am just showing. Let us here we did the welding operation, then especially in case of mild steel types of structure, how the residual stress is distributed in a steel structure, that I am going to show you. So, here you see. So, this axis represent the distance and this axis represent the what it is called stress. So, what we observe, it is generally tensile in nature along the weld zone and it is near to the welding zone region. What happens, what I am telling you understand, which is subjected to shrinkage types of force during cooling cycle, that zone generally it is subjected to what it is called tensile types of stress. Now, you see, as residual stress is a balancing force, so this weld zone is subjected to some tensile force, but this force is supported by the surrounding material, then the surrounding material will be subjected to some compressive types of force, or you can say compressive types of resisting force, or you can say compressive types of residual stress. So, that is why what happens, the surrounding material, here the residual stress will be distributed like this. Let us, this plate has this much of length, a particular portion I am just showing. So, how this residual stress distributed? So, you see it is distributed like this. Now, this is this side also it is distributed like this. So, this is called tensile or positive stress and this is negative types of stress. So, whatever the tensile summation of all, if you just take the force about any section, then what happens, then we will get summation of all forces acting and summation of all moment acting in this section will be 0, because this is in self equilibrium condition, this you should keep it in mind. So, whatever the proportion of tensile stress will be developed, same proportion of compressive stress also will be developed there, then only it will be in equilibrium condition. You can observe here, it is generally tensile in nature, what it is called, it is generally tensile in nature near the weld zone, and away from the weld zone it is compressive in nature. Now, residual stress can have different types. Type in the sense, this residual stress further categorized into 3 different categories depending upon the direction. This is generally, one is called longitudinal residual stress, longitudinal residual stress, second one is called transverse residual stress, and another one is called through thickness residual stress, or that is sometimes called short transverse residual stress. What it is called? Short transverse residual stress. How it is, little bit I am just showing. Like what happens, residual stress which is acting, let's, this is a plate, let these 2 plates we join together here, Let's we did the joining operation here. This is the well bit. So here you see this is the well bit here. So this is the welding direction. So in welding direction, whatever the stress we get, this is called longitudinal stress. So this is called longitudinal stress. Transverse stress is perpendicular to the weld direction. Perpendicular to the weld direction means this direction is called transverse stress. This I am representing number 2. And through the thickness, whatever the stress we get, that is called short transverse stress, that I am representing number 3. Generally, the magnitude of this longitudinal residual stress is high compared to short transverse and short transverse residual stress. This you should keep it in mind. Why? You see, in this well bit, if you just take the well bit cross section, you will get well bit cross section like this in longitudinal direction. In longitudinal direction, if we take the cross section, let us I am taking a cross section XX. So in this case, the longitudinal cross section is like this. If we take a transverse cross section here, if we take a transverse cross section in this well bit, let this is I am just representing YY, let us YY cross section. In this case, we will get a cross section throughout the length of the plate like this. Just if we compare in this way, that means in welding direction, the cross section which is supporting this sinkage types of force, or you can say the restoring force, that cross section is, let us say, along for this transverse direction, for this transverse residual stress, if we take the cross section. So this is, you can say, longitudinal cross section, you can say, the list I am representing A1, and this I am representing this for transverse cross section, let this is A2. Now from here itself you can get an idea, this transverse cross section which support this sinkage types of force, that means well bit region generally subjected to sinkage types of effect or compression type or expansion types of effect, correct. That is why what happens, we have to consider that cross section only. So if we take this cross section, here we will get a cross section which is A1. Now here you can see this A1 is much smaller, you can say like this, smaller than A2. That is why what happens, we know what is stress, we know stress is equal to this force by cross sectional area. So you see, so if this is a stress, now let us I am just representing sigma L is longitudinal stress, here I am representing sigma L longitudinal stress, this is let us sigma T transverse stress. So you can see this longitudinal stress will be your this sinkage force, or you can say sinkage force divided by well bit cross sectional area, longitudinal cross sectional area, you can say this A1. So whatever the value we will get, this will give you the longitudinal stress. Similarly, sigma T transverse, here also this sinkage force divided by A2 if we put. Now as this A2 value is much higher than this A1, that is why you can say this sigma L is comparatively much greater than this sigma T, as well as you can say this short transverse stress further less than transverse stress, that you can say. So how this magnitude is varying, I think that idea you got. Now we will show you how this longitudinal stress distributed over a seam of this weld, that I am going to show you along the length of the well bit, how this longitudinal and transverse residual stress is distributed, that I am going to show you. So what idea you got? You got the idea how the magnitude of residual stress dependent. So magnitude of residual stress dependent on the cross sectional area of sinkage zone, you can say sinkage zone. That means the well bit which is subjected to melting and solidification, that zone generally subjected shrinkage types of effects. So in that zone we have to take the cross section, once for longitudinal direction, another for transverse direction, another for plane direction for short transverse stress calculation. So there we observe that this A1 is much smaller than A2. That is why we can say that this way we can, if we just say that transverse stress magnitude is smaller than longitudinal stress. So, along the well bit generally how it is varying, that I am just going to show you. Let us this axis represent welding direction, let this axis represent y direction. Okay. Now, how along this y direction, how this stress is distributed, this is y direction. So, let us here I am just representing, this is the stress. So, if we just draw this thing, then we will get generally at the end the residual stress generally gradually increasing at the middle section, where generally it is more or less uniform. After that you see it is again almost becoming to 0. What I am telling, understand, that means at the middle zone this residual stress distribution more or less uniform in nature, because in this initial zone here you can say this weld zone is if we just categorize this weld zone, we can categorize in 3 different zone. Like what happens, this initial zone where the temperature, once the welding just started, at that time generally temperature start gradually increasing in nature. That is why what happens in this zone, at a particular zone you can say where the temperature is gradually rising in condition. So, you see, so this zone is called initial transient zone. What it is called? Initial transient zone. What I am telling, understand? This zone is called initial transient zone, and this zone is called final transient zone, where once the means welding is going to completed, at that time generally here the temperature gradually decreasing nature. That means with time the temperature is gradually decreasing. So, once something is varying with time, that is called transient phenomena. This you should keep it in mind. So, that is why here this is called, you can say, final transient stage. So, in final transient stage also you see as the temperature is gradually decreasing, after that it goes to room temperature, and here as there is no what is called end of the plate, here again the residual stage becoming around 0. What I am telling, understand? So, close to 0. Now, in between this zone where generally the temperature remain almost uniform actually. Here generally throughout the entire zone almost temperature distribution, peak temperature distribution you can say almost similar. So, this zone is called quasi-static zone, or you can say this zone is called, what it is called, quasi-static zone. So, as here, so it is here as this first zone is rising temperature zone and end zone is decreasing temperature zone. That is why here that residual stress gradually first year's residual stress gradually increasing, then at the end residual stress gradually decreasing and goes to around 0. But in the middle zone it is almost uniform in nature. Let this is your longitudinal residual stress sigma L. Now, what will be the what it is called transverse residual stress. So, here the transverse residual stress throughout the interval zone will be generally its distribution is like this. That means what it is called, its magnitude, this is the transverse residual stress distribution. Just roughly I am drawing these things, transverse residual stress distribution. So, this transverse residual stress distribution here generally its magnitude is much lesser than sigma L value. Just I am going to show you some means idea of how the residual stress distributed along the interval length. So, here also if we draw the transverse residual stress distribution, here we will get just generally transverse residual stress distribution, which is we can just here I am just showing, this is like this. That means, this transverse residual stress distribution over the interval plate, it is generally what it is called almost tensile in nature, and its magnitude is much smaller than this what is called longitudinal types of residual stress. Okay. This you should keep it in mind. Now, we will discuss what are the factors influencing this residual stress. Generally there are different types of factors which influencing the residual stresses, like the residual stresses depends on what types of material we are going to weld, then what types of welding sequence we are using, and what are the different types of support we are providing to prevent the movement of weld structure, and to align the weld structure, what are the different types of tack welding we are providing. So, depending upon different parameter, this welding residual magnitude varied. This you should keep it in mind. Now, like how the material property affect the residual stress, like first material property, generally to rise temperature in a particular plate, first thing required is what are the parameter affect the temperature distribution. First of all we should know this thing. So, that is why here I am just showing, we know that Fourier heat conduction equation. What does Fourier heat conduction tell? We know that K del 2 T by del x square plus K del 2 T by del y square, if the material is what it is called homogeneous types of material, isotopic homogeneous material, they are generally K is same throughout the all direction. That is why here I am writing like this, K del 2 T by del z square, this is equal to, we know, rho C del T by del T. So, these are the governing equation we can say for finding out the temperature distribution once it is subjected to some external types of load, correct. So, external types of heating load. So, you see this T is called temperature, K is called thermal conductivity, and rho is called density, and C is called specific heat. So, this is very well known to you. So, I am not going in detail. So, to find out the temperature distribution, what you can observe from here, you can observe this temperature distribution T is depends on, T is, you can say T is proportional to rho C by K. So, it is generally proportional to a specific heat, and it is inversely proportional to thermal conductivity. So, you see generally, so to rise temperature in a plate or in a welded specimen, first thing depends on its thermal conductivity. So, what happens if the thermal so in a structure, if the temperature rising is more, that means then there will be more what it is called temperature gradient, you can say. If the non-uniform types of heating in case of welding especially, because if the thermal conductivity will be more, then what happens from itself, this relationship itself we can got an idea. That means how the material property affect this what is called affect the residual stress distribution. So, residual stress distribution depends on first temperature distribution. So, here you see if K is more, from this relation itself we can get K is more, then we can say that for keeping all other parameter constant, then your temperature will be less, higher that K, lower the temperature. So, in a structure if the temperature rise is less, then definitely in a material if the temperature rise is less, then there will be less thermal expansion, or you can say there will be less thermal gradient. Due to this thing there will be less expansion and contraction types of phenomena. So, there will be less residual stress. That things you should keep it in mind. So, here the first and foremost material property which affect the residual stress is, you can say, thermal conductivity. So, higher the thermal conductivity, lower the residual stress, because higher the thermal conductivity, lower the temperature rise. So, lower the temperature rise, lower will be the expansion, contraction, other phenomena. Then what happens? You can say your residual stress also will be less. So, another parameter is, you can say, specific heat. So, temperature is directly proportional to specific heat. So, higher the specific heat, higher the temperature. So, you say that means residual stress is more or less proportional to a specific heat, you can say. So, similarly residual stress is also inversely proportional to thermal conductivity. This idea you got. So, you see, so temperature distribution in the weldment is determined by thermal conductivity and thermal diffusivity. K by rho C is called thermal diffusivity. This you just keep it in mind. What it is called? K by rho C is called thermal diffusivity. This you just keep it in mind. So, from here also you got the idea. So, higher will be the thermal diffusivity, lower will be the temperature rise, you can say. Then what happens? You can say lower will be the residual stress distribution. From here you can get that idea. Okay. Now, it is also depends on thermal expansion characteristics of the material. Thermal expansion characteristics of the material, in the sense like what happens, we know a material have some thermal expansion coefficient. So, if a material have more thermal expansion coefficient, then we know this thermal strain ET is depends on your thermal expansion coefficient alpha into temperature difference delta T, correct. So, higher the thermal expansion coefficient, that means if this thermal expansion coefficient more, then you see thermal strain is more. So, if the strain is more, then there will be more contraction and expansion types of phenomena. So, there is a chance of more residual stress, correct. So, it is depends on thermal expansion coefficient also. Now, it is also depends on what it is called mechanical property at elevated temperature. Elevated temperature means what happens at high temperature, because material property is temperature dependent. So, at room temperature you will get one types of material property. Generally, if the temperature increase, this material property is varying. Like let us I am considering Young modulus. So, if a Young modulus in room temperature, it will have some magnitude. At if we increase the room temperature, then what happens is Young modulus generally varied. Generally, with increasing temperature, this Young modulus is gradually decreases. Now, here one thing you keep it in mind. So, with temperature means at elevated temperature, at high level of temperature, if the material have more Young modulus, that means mechanical property, then that material generally at elevated temperature will rise more residual stress. What I am telling, understand, that is why you should keep it in mind. Whenever some material have a mechanical property which is more, especially Young modulus more at elevated temperature, that material has a chance to develop more residual stress. Because why it is more? Because you know stress is proportional to what is called strain. So, once you just make it equal, this sigma equal to your E into epsilon, because we know residual stress is depends on what it is called elastic strain. This you should keep it in mind. Residual stress is depends on elastic strain, because what happens once you release that portion, or that means once you just leave that sinkage portion, or you can contraction what it is called expansion portion, then what happens, this material is returned back to its original position. That is why you see residual stress is developed inside a structure due to elastic strain. This you should keep it in mind. Again and again I am just telling. So, this elastic strain range generally in elastic strain range, you know, which follow the Hooke's law, correct. X till proportional limit, actually we follow the Hooke's law. That is why you can easily find out, once we can able to find out this elastic strain magnitude in this lock-in stress zone, then you can easily find out what is the stress value. Now, here you see this stress is further depends on another parameter, that is called Young modulus. So, this stress is also directly proportional to Young modulus. So, higher will be the Young modulus at elevated temperature, higher will be the residual stress. This you should keep. So, this relationship also you are getting from here. Everything is well established on. Just you have to refresh this thing, then you will get all the idea how the residual stress varying. So, that things only here I have written. So, material properties, especially material with large Young modulus and coefficient of linear expansion, that means alpha, then what happens, this welded residual stress will be higher in magnitude. This you should keep it in mind. Now, also I have written, we have observed that thermal conductivity have inverse effect on temperature distribution. That means higher the thermal conductivity, lower the temperature magnitude. So, lower will be the what is called thermal expansion and contraction, then lower will be the residual stress. That is why here I have written conductivity increases, residual stress decreases. It is also depends on different types of welding sequence. Welding sequence generally what happens, it has observed that if we can generate during welding operation some balancing types of welding sequence, then what happens is we can control the residual stress significantly. How it is, that I will show you in subsequent slide. This residual stress also depends on variation in sinkage, then its phase transformation and welding tack. This phase transformation related thing I have already explained in last lecture. So, we know once a material is subjected to rapid means heating and cooling, then what happens due to this heating and cooling, this different types of phase of microstructure changes is occur, correct. Like what happens, austenite structure change to ferrite, perlite, bainite, martensitic types of a structure. It depends on cooling rate also. So what happens, so different phases have different types of volumes. That is why what happens, due to the change of these different volume, there can be developed what it is called type 2 types of residual stress, which I have already discussed in last lecture. So that things already I have explained, because due to these different phases, different expansion contraction is taken place. Due to that, what happens, there can be chance of locking types of stress in these different phases, okay, which can raise the residual stress. It also depends on welding tack. Always you should keep it in mind. Generally, what is welding tack? Welding tack is generally what, we are going to join two different material piece, correct. So once we are going to join two different material piece, generally to provide the filler material in weld zone, there is required to put some gap in between two plate, correct. Sometimes generally if the plate thickness is little bit higher, then there generally these types of what it is called, this types of root gap is required. So this is called root gap types of, or you can say gap between two workpiece. Why this gap is provided? Because not to provide short circuiting types of phenomenon, and what it is called, to fill this gap by using so provide this filler material properly. That is why this gap is provided. To make this gap properly, there is required to provide some small type of weld deposition. So these are called tack weld, because this tack weld is required to use to align the workpiece properly. So that what happens, this gap remain maintained. As well, we want to make a T section to position this T like this. This is one plate, over this plate we want to plate another plate, correct. So another plate or bar you can say. So this bar plate, generally what happens, this is the length of this plate bar. So what happens, to align this T plate in this lower plate, there is required to put some tacking at otherwise what happens, this vertical plate will not be aligned in this lower plate. These are all called tack weld. So always you should keep it in mind. Generally during welding operation, there is a chance to crack this tack due to this expansion and contraction phenomena during heating and cooling cycle. This crack tack is the huge stress riser. That is why once we go for doing the welding, first of all we have to remove this what is called tack, or you can say crack tack, by using melting or by using some other removing operation. Okay. This you should keep it in mind. These things I have written in subsequent slide that I am just showing. So here you see what are the factor influencing the residual stress, that idea you got. Now we will see how to control this residual stress. So residual stress can be controlled by designing the what it is called joint geometry, also by designing the what is called different types of tacking sequence. Also we can, once some residual stress already develop inside a welded structure, from there also we can eliminate the residual stress. How? By using some post weld heat treatment technique. So that related things also I will discuss in subsequent slide as well as in subsequent lecture in details. So first of all, to control the residual stress, first and foremost things is to design the joint geometry. Here always you should keep it in mind, like what happens, we should design the joint geometry such a way so that there should develop some balancing types of stress distribution, because so that one stress will just nullify the other stress component. That way we can say, like if we instead of first things, instead of doing what it is called single V types of bar joint, if we just do double V types of bar joint, if we just do double V types of bar joint, then we can you can imagine we can control the residual stress distribution significantly. How it is, this a little bit idea I am just going to show you. Like here you see especially if we just do a single V bar joint in a plate, there whatever the volume of material required, this you should keep it in mind, volume of material requirement, that volume of material generally you can say much higher than that double V types of bar weld joint, because you see let this volume of for single V is V1, this is generally you can say much higher than what it is called V2. V2 means this double V bar joint. So, due to this volume of molten material related issue, so in single V there will be developed what is called more sinkage or sinkage types of force, or you can say thermal expansion as well as contraction types of force in this weld zone. So, during cooling as more contraction force will be developed, so in this single V bar joint there the residual stress distribution will be more, as here the volume of material in double V is less, as well as about this neutral axis, neutral axis means through the thickness at middle zone. If you just find out the what it is called bending stress distribution, there you can observe that this bending stress generally through the thickness it is distributed generally here in this zone, the bending stress is almost 0. That means you can say where the bending stress is 0, that section or that line you can consider is called neutral axis. So, you see so this neutral axis, about this neutral axis if you just see, so here due to this top side, here you see this top side in case of single V bar joint, there will be volume of material, like let this is the volume of material at top side and this is the volume of material in bottom side. So, once this once the sinkage is developed, that means during cooling once sinkage is developed, as the volume of material at top side is more, that is why here you say top sinkage force will be more, but below this neutral axis as this volume of material is less, here the bottom sinkage force let this F2. So, as the volume of material at top side is higher, that is why we can get F1 is much higher than F2. Okay. That is why what happens due to this unbalanced force also what happens you can see, and as the volume of material is more in this single V, there will be developed more, it is called residual stress. Whereas in double V bar joint, as about neutral axis more or less equal amount of will be this there, that is why top sinkage force and bottom sinkage force in case of double V bar joint will be more or less balancing type. That is why what happens in this double V bar joint, at the volume of material required is less, as well as top sinkage and bottom sinkage things is almost balancing in nature. That is why here residual stress also will be less. That is why here you see we should choose such a joints so that it should balance each other. This you should keep it in mind. Now, another things, we should choose the joint geometry in such a way where the volume of material required should be less. So, that is why instead of going for V bar joint, if we just make some U types of bar joint means like this U shape bar joint. So, let this is your V bar joint, this is U bar joint. So, whatever the volume of material required to weld by using V bar joint, the volume of material required for U bar joint will be much smaller. This you should keep it in mind. That is why instead of using V bar joint for especially thick section, if we go for U types of joint, there the volume of molten material required will be less. So, if the volume of molten material requirement will be less, then whatever the sinkage force will develop during cooling of that volume of material. So, whichever have less volume, there will be less sinkage types of force. So, less sinkage types of force will develop less residual stress than V bar joint. This you should keep it in. That things only here I have written. The use of U groove instead of V groove reduce the amount of weld material. So, if the weld material is less, so expansion contraction phenomena during cooling, generally sinkage force will be less. So, residual stress development will be less. So, here I have shown that there is some special types of welding sequence which can have a significant effect in welding residual stress distribution. It is observed that by using back step, then symmetric types of welding sequence which reduce the welding residual stress significantly. How it is, that I am going to show you little bit, then it will be more clear to you. Like symmetric types of welding sequence, how it is look like. Here I am just showing. Let us along this we are doing the welding. So, symmetric types of what it is called welding means it start from middle, let this is one first pass, then first progression of weld, then this is second, then again this is third, this is fourth. This is called what it is called symmetric types. I mean means about the center line, if we draw center line, both side, this my first left side, then right side, then again left side, then right side, the symmetric types of welding operation. It is observed that due to this symmetric types of welding process, there we can reduce the welding residual stress significantly, because there is occur some balancing types of stress distribution. What I am telling, understand, which affect the residual stress distribution significantly. This is called symmetric types of welding sequence. Now, back step types of welding sequence, how it is look like. Back step types of welding sequence is, here I am showing, let this is to workpiece, here I am going to do the welding in this direction. So, this is your welding direction, I am writing WD, but here how the welding is done. So, welding is done. So, welding is start from, like this is welding pass 1, this is welding pass 2, this is welding pass 3. So, progression of welding is that means right side, but how the welding is done, but welding direction generally here you see this welding direction is leftward direction, that means in back step direction, but it is gradually progress in right side direction until it is completed. What I am telling, understand? This is called back step types of welding. What it is called? Back step types of welding. So, these are the welding sequence. Once we follow, there we can control the residual stress significantly. Now, here another things you should keep it in mind. Always we should prevent, actually always we should avoid any types of bending stress in a welding structure. So, whenever we go for doing welding operation, we have to check whether there is any types of bending types of effect is there in this welding zone or not. So, always you should keep it in mind, the introduction of bending stress in a weld should be avoided. This you should keep it in mind. So, these are different types of welding sequence. Also I have shown you how its effect, that also I have discussed. Now, the control of residual stress, what are the other parameter effects? Like I have already told you, the residual stress is depends on mechanical property. The mechanical property means Young modulus, yield stress. So, Young modulus related things I have already discussed, that how the mechanical property affect the residual stress. In previous slide I have already told you how the Young modulus affect the residual stress. Now, like Young modulus, what it is called yield stress also have significant effect in residual stress distribution. This you should keep it in mind. Like this yield stress also is a very important mechanical property, correct. So, it is observed that once some material have high yield stress at elevated temperature, this you should keep it in mind, that because this yield stress also depends on temperature. So, if some material have a yield stress high at elevated temperature, in that types of material there is a chance of high locked in stress. What I am telling, understand? That is why whenever we go for choosing a structural material for welding, that a material we should choose such a way so that its yield stress should be what it is called optimum at the, you can say, at the at elevated temperature. So, that types of material, as well as whatever the filler material we are going to use, that filler material also we should choose. That means it should not have, you can say, high yield stress level at elevated temperature. So, that things you should keep it in mind. So, I have already told you that stack attack also have a significant effect in residual stress distribution. It is observed that crack types of tack if there is in a welded plate, then there is a huge rise of residual stress. That is why crack tack weld should be chipped or melted out before welding the work. This you should keep it in mind. If welded structure are prevented from moving by tack or clamping or jigging operation, then generally the amount of residual stress that remain will be high. So, these things also you should keep it in mind. If the welded structure generally if we are going to prevent its deformation, restraint types of effect, that means higher will be the restraint in a structure, higher will be the residual stress. This you should keep it in mind. So, always keep this thing in mind, as much as possible less restraint you should provide in your welded structure, then what happens, there will be less residual stress, because it will free to expand and free to contract. Then restraint types of effect which generally create internal stress, that things will not be there. So, once something is free to expand, free to contract, there the residual stress will be minimized. That is why I have already told you, if uniform heating and uniform cooling without any restriction or without any types of fixturing, there will be almost zero residual stress. Okay. Now, let us in a structure some residual stress already develop. So, how to minimize the residual stress? Yes, there is also some procedure. This residual stress we know we can minimize by introducing some opposing types of stresses. Like what happens, we know that in weld zone generally there is developed, in case of a structural steel there is developed generally what it is called tensile types of stress. So, if we can develop there some compressive types of stress, then what happens, we can nullify, or you can say we can mitigate, or we can say we can minimize the residual stress. That is why that things we can do by using some what is called mechanical types of operation, that is called pinning operation, or you can say some short blasting operation. So, these are the different types of operation. Once we do this thing, then there is developed some compressive stress. So, due to this compressive stress, this tensile stress is you can say mitigate or minimize. Okay. Now, there are some other technique also there by which we can relieve this residual stress, that is called heat treatment process. So, by different types of post weld heat treatment technique is there, that means after welding if there is some residual stress, that we can minimize or relieve by using some heat treatment process. The heat treatment process follows some controlled heating as well as some controlled cooling phenomena. Okay, that is called post weld heat treatment process, that also I will discuss in subsequent lecture. So, now what is the effect of residual stress in distortion? What I have already told you. So, higher will be the restriction, or higher will be the support, or higher will be the fixturing in a welded structure. More will be the what is called restoring types of force develop, and it will be locked inside, correct. So, more will be the residual stress, but what happens if we use more fixturing or restraint in a welded structure, your deformation will be less. So, here one thing you should keep it in mind, higher the restraint, deformation will be less, but more will be the localized types of residual stress. This you should keep it in mind. So, conversely we can say low restraint tends to increase the distortion, because if there is less restraint, it will free to expand, contract, and then there is a chance of what it called more deformation, but what happens there, the residual stress, that means will be less. Now, these are the methodologies which I will follow for prediction of residual stress. This I will discuss in next lecture. Just I am introducing what are the different types of methodology generally used to predict the residual stress. Especially to measure the residual stress, there we can use different types of techniques. One technique is called, like we can measure the residual stress, or we can say we can calculate the residual stress by analytical method, we can calculate the residual stress by numerical method, and there is some direct calculation by using some experimental method, that is called experimental method. So, analytical method means here some direct formula is there, by using that formulation we can predict the or calculate the residual stress. Numerical method, there is some approximate method, that means which will give that approximate value of residual stress, like finite element method, finite difference method. These are the different types of what it is called numerical method. By using this numerical method we can predict the residual stress, and in experimental method like here by doing some experiment we can also predict the, or you can say find out the residual stress. Now, in numerical method generally the method which is used for measuring residual stress is called thermomechanical analysis, and for experimental method there are different types of method which are used, like there can be destructive technique, there can be non-destructive technique, there can be what is called semi-destructive technique. So, related to all this methodology of measuring residual stress which I will discuss in next lecture. So, thank you.